I'll work on it. Well, aloha, because this is a presentation on waves, specifically the electromagnetic spectrum. What this is an overview. I'm sure you've seen it several times in your scholastic careers. That just goes through an order from low energy to high energy, the waves on the electromagnetic spectrum. And what I'm going to do is just go through and give a couple of examples of each type, their relative wavelengths, or their absolute wavelengths, the amounts of energy they have relative to each other. And I don't know, just getting used to or reintroduced to the various waves on the electromagnetic spectrum. Longest wavelengths first are the televisions and televisions and radio waves. Thanks. These very long, and you guys know wavelength is proportional to energy, but inversely. So the longer the wave, the less energy it has. And these TV waves are thousands of meters in length from crest to crest, trough to trough, whatever. They're very, very long. So thousands down to hundreds of meters. So very low energy, but they were some of the first to be utilized, and that's why, because they weren't that hard to generate. And then once we get a little shorter than the TVs, you'll get old school radios, and we have FM and AM waves. The AM waves are hundreds of meters in length, so we're talking a couple of hundred, 400-ish meters in length, which is pretty impressive. FMs are a little shorter, they have more energy in them. Those are a couple of meters, 2, 3, 4, 5 meters ish in length, are the FM waves. And we keep going a little shorter than that. There's quite a gap between the radios, but then we get into what are called microwaves. These particular waves are 10 down to a couple of centimeters in length, so they have a little more energy. What these are designed to do is resonate with water molecules. That's really all they do, is get those suckers to dance. But when these guys came out, they thought, oh my gosh, they're going to change the world. People were pretty scared of them, but there's really nothing to be too scared of. They don't have enough energy in them to really do much outside of their enclosed area. There's nothing to be too afraid of. If you keep going a little shorter than those, or in ish the same area, the infrareds, between a microwave and infrared is where you'll get these cell phones. And I just found pictures of some very old school cell phones. I'm sure your parents had one of these. If you see some old movies from the 80s, you'll see some of those in TV shows. But anywho, these are kind of ish in the microwave to infrared-ish range. These waves that you're getting hit with them right now, I promise. So there's some of those. If you've ever used anything with a remote control, you're going to be in the same kind of ish range, in those same wavelengths and same frequencies. So I think the next one is a bunch of remote controls too. Yeah, I don't know. In case you didn't know what a remote control looked like. And I think I have one more. I don't remember. Oh yeah. Anything with a remote is in this region, between microwaves and infrared waves, and it's a pretty large section of the spectrum, from tens of centimeters down to millimeters and some micrometers even. We're getting pretty small, but once you get a little smaller than this is when you start to feel the wave, because infrared is what you're giving off right now. It's what everything that's above absolute zero in temperature gives off right now. And so the joke phrase I use is, you can't see infrared, but the predator can. And this is obviously a heat signature. So an infrared wave is a little shorter than microwaves. It's what you feel is heat. Um, and we're talking tens ish of micrometers is how much these guys have in them. And I think the next one is a night vision goggle. Yeah, the way these are applied is all they do is they catch infrared, and they have software in them that just transfers an infrared wavelength into a different temperature that gives you, just changes it from an infrared wave to a visible wave so you can see it. That's really all they do. And they do them very well. That's okay. This is a picture of one of my favorite bath toys when I was a kid. I used to play with toasters. Um, but anyway, the reason I have that here is what you feel is heat, what those copper coils, or what those nichrome really coils inside a toaster do. You can feel them get hot before you actually see them glow. And so the infrared has less energy. And once you can see them glow, they're enough energy to become visible, which is, I think, the next one. Yeah, on a stove. You can feel the heat before you can see the heat. So it takes a little more energy to become visible and shorter wavelength still. So we're down into nanometers now. But something like this, when they say if you see it, it's glowing red hot, whatever, that means it's hotter than when you can't see it. And I think the next one is the actual rainbow. Yeah. So these, I know you've heard the Roy G. Biv your whole lives. What I would just add to that is that the red waves are the longest, and the Roys, the Gs, the Bivs are the shortest wavelength. So there's more energy in a violet, less energy in a red wave. We're at 700 ish, and now we're down to nanometers for visible light. 700 ish on the red, 400 nanometers way down on the violet end of the spectrum. So more energy in violet waves, and as we get past the violet part of the visible spectrum, you're getting into some things that you're probably going to get a little more scared of, but in terms of how much energy they can have and with them. But this is just another application of something glowing in UV. If you hit them, it's all these glow in the dark types things. We're giving them enough energy to glow and give their own stuff back. So any things like that you're hitting with black lights, you're focusing on those types of waves. And the next one, I've probably seen these in like crime videos or TVs or movies or whatever, but again, they're just hitting them with UV. And what that energy does is cause the molecules inside here to give off their own waves, and you can hit things with enough energy to make them glow themselves. So there's more energy in the UV part of the spectrum, and I think, oh yeah, this. You've probably heard of UV indices that tell you on any given day how scared you should be of sunshine. Low isn't that big of a deal, and tens and 11s are a much more extreme day to say, hey, stay out of sun because physics happens. But sunburns can happen. This next one is even more worse than that, and you start getting blistering and what have you. But the UV waves have enough energy in them. You're talking barely tens of nanometers there, but when they hit you, they have enough energy to literally cook you, and that's what's happening. So their energy can go into you skin deep ish. They don't have much energy to go any deeper than that, but they can certainly transfer some energy into you there. And then if you get even shorter wavelengths, then you're getting into X-rays. So they have even more energy in them. They can go right through your soft tissue, right through your skin. Don't have enough energy to go through bones. They'll bounce off that. And so I just swiped a bunch of images of various X-rays just to show you, you know, physics, I suppose. The next one, I don't know if that's even real or not, but who knows? Up until this point, the X-rays, those are again what we said, even more energy than the UV, so they're even shorter of a wavelength. We're into the hundreds of picometers, which means 10 to the negative 12th. So X-rays and everything up to this point come from electrons jumping down energy levels. So every photon we've talked about to this point owes its origin to an electron. Once we get to gamma radiation, those have more energy in them than an electron can give, so they have to come from a nucleus. So I'm sure you recognize pictures like this. This is an example of, obviously, a nuclear atomic bomb during its testing era. A lot of energy. We're talking in the single picos. I'm sorry, keep going. And these were just more pics I swiped from some old history websites. They will have these waves have enough energy that when they hit you, I mean, they basically kill you instantly. They don't vaporize you as per se, but where these shadows are is where something used to be that absorbed that radiation. And so these pictures just show you, hey, there's sometimes physics happens for not the best of reasons. And if we keep going, the next one, I put this one on here. Just art imitates life, and those were dropped in the 1940s. The Godzilla, late 50s, mid 50s is when these movies first came out, and it was just an artistic expression of what can happen when there's a lot of radiation off the coast of Japan. And the next one, I think, is, when they started doing these types of comic books dealing with the gamma waves. Those were what made the Hulk incredible. But this was the early 60s when this was coming out, so in a nuclear era, when just learning about the technology here. And I think the next one, gamma waves being given off in black holes is a very big part of astronomy. There's more energy in one of these is a quasar black hole system flying at us. Folks study those at what are called gamma ray symposiums, which study images of centers of galaxies in the gamma wave part of the spectrum. And what was the last one, I think, is, the Gamma Ray Symposium. Even in Alabama. Geesh. But anywho, please just remember, parts of the spectrum, just because you can't see them doesn't mean other people or other items can't. They're certainly out there. And just remember relative energies to one another. But shorter waves, more energy, higher frequencies. You know that because they all travel at the same speed, which is 3e8. They all travel 300,000 kilometers per second, or 3e8, 30 million meters per second. Please remember that number. And so shorter waves, higher frequencies are the ones you're a little more scared of. Aloha.